The next presentation is Building Deterministic and Concurrent Flight Software Using Lingua Franca and PretVM by Shaokai Lin.
All right. Are we good to go? Okay. Can people in the back hear me? Good. Wonderful. All right. So hello, everybody. My name is Shaokai Jerry Lin. I'm very excited to present in front of you today. The title of my presentation is Building Deterministic and Concurrent Flight Software Using Lingua Franca and PretVM. To quickly introduce myself and my collaborators, I'm currently a PhD candidate at UC Berkeley, and I'm very fortunate to work with Tassilo Tennenberger from TU Dresden in Germany, and I believe he's currently online. Also Erling Gjellam from NTNU in Norway, and my advisor, Edward Lee from Berkeley. And of course, this work would not be possible without many contributors for this open source framework called Lingua Franca. And at this point, Lingua Franca has many contributors from around the globe, spread across different universities. Okay. So in this talk, I will break the talk down into 3 segments. And let me first start by introducing the research problem. So the central research question we're interested in is how to manage the challenge of concurrency in space applications. As many of you may agree, concurrency can significantly complicate system design, especially for mission-critical systems like space applications. Well, in this case, reproducibility is a big challenge. The reason why it is important is that reproducibility makes testing useful. Testing would not be effective if the software behaviors cannot be consistently reproduced. However, in this case, reproducible behaviors are hard to obtain when the system is concurrent due to potential race conditions. To show you a concrete example, let's focus on the diagram on the right. So let's assume that on the satellite, there's an internal routine task called calibrating sensors. And let's label that as task A. And at approximately the same time, there is a command sent from the ground labeled task B for changing the attitude of the satellite. And now the question is how to properly handle these tasks. So in this scenario, order really matters here, and different orderings may lead to different behaviors. Given random communication delays, there are 3 possible behaviors. So scenario 1, tasks A and B are processed at the same time. In this case, I would argue that this is not the most ideal scenario, right? Because we don't really want to change the attitude while we calibrate sensors. We wouldn't be successful at both tasks. The second scenario is task B is processed before task A, which means that we change attitude before we calibrate sensors. That also doesn't seem quite ideal, right? Because we don't want to change attitude with uncalibrated sensors. And scenario 3 is task A is processed before task B, and this seems to be the best behavior out of the 3, right? We first calibrate the sensor, then we change attitude. And now, tying back to the reproducibility question, how should we consistently reproduce this 3rd behavior, which is the behavior that we want? Unfortunately, the operating system offers limited support. To do this, the user will usually need to augment the application logic manually to deliver the reproducible behaviors. All right, so on the right-hand side, the user can write a function for changing attitude and a function for calibrating sensors. And the user will also provide a process function, which could set up a queue of commands and reorder these commands if an undesired pattern of commands is detected. And what complicates this picture further is that the primary programming model on an operating system is threads, which could be hard to guarantee correctness for. At the bottom, there is a paper called The Problem with Threads, which discusses this exact problem. I would also like to motivate for the need for a time-centric model. So in a classical real-time systems development, people usually follow a bottom-up approach, which means that we first start with an implementation. This could be an existing scheduling algorithm, like earliest deadline first. We implement the system, and we observe the timing behavior arise from that implementation. And then we check whether high-level deadlines are being satisfied. If so, then this design passes the validation and can be deployed. If not, we go back to the implementation and repeat the process. We refine the implementation and do this again. So this is a bottom-up process. A time-centric model, on the other hand, enables a top-down approach, as shown on the right. We first start with a set of timing specifications, which are the correct behaviors that we define. Then it's the compiler's job to check whether these specifications are satisfiable. If so, the compiler synthesizes a correct by construction implementation. If not, we go back to the timing specification and refine them. So by starting with the high-level timing specifications, the compiler ensures that the implementation conforms to the timing specifications, reducing costly and error-prone rework. So next, I'm going to talk about Lingua Franca, which is our main project at Berkeley, and a recent development called PretVM. So what is Lingua Franca? Lingua Franca is a polyglot declarative coordination language for real-time, concurrent, and distributed systems. Wow, that's a mouthful. So let me show you a concrete example what I mean. So there is a classic cyber-physical systems example, CPS, which consists of some sensors, some processing logic, and some actuators. So in this case, we have two sensors operating at different frequency. They both are fed into a processing logic processing unit, which performs sensor fusion and makes a decision on the sensor values and further drives the downstream actuator. On the left-hand side, you see an almost complete Lingua Franca program that correspond to this system on the right. So what we do first on line 1 is to declare a target language. In this case, the target language is C. What this means, I'll come back to this later, is that you can write the application logic in C code. And on line 3, because we have two sensors here and they're essentially the same type of sensor, we can define a class, a reactor class called sensor. So everything in this picture on the right here are reactors. And reactors are stateful containers with reactive code blocks. So in this reactor sensor, we can essentially start by writing reactor and then give it a name, sensor, and define an argument called period of type time. And this period argument is initialized to 100 milliseconds. So as you can see right off the bat in Lingua Franca, time is a first-class citizen, and you can directly specify time and manipulate time. And reactors are stateful, and they can communicate with the outside world through ports. On line 4, we declare an output port called out with a type integer. We can also further give a timer called T on line 5 that starts at T equals 0 with a period of the period argument that's specified on line 3. And then, of course, being stateful, we can give a state variable called count, CNT, that's of type integer, and we can initialize that to 0 on line 6. And we can further specify reactive code blocks called reactions on line 7. And this reaction is sensitive to the timer firing T, so we write it inside the parentheses. And we also specify a list of potential effects by writing down an arrow sign and then a list of things that this reaction can modify. In this case, this reaction can modify the output port called out. And then you see an interesting looking bracket that starts with a curly bracket followed by an equal sign. This is where the target language comes in. So essentially, the user can write any C code within this bracket. And this is the application logic of our system. Yeah, so if it's a sensor, you can use memory map IO to grab sensor value from peripherals. This is where you do that. And we can do the same. We can define the processing unit and the actuator in a similar manner from line 9 to line 18. And then what's being left is to instantiate these instances and connect them, which is what's happening from line 19 to 27. So as you can see, we instantiate two sensors, an S1 and an S2, and we passed in two different periods. And Lingua Franca semantics will guarantee that for every sensor value of S1, this sensor value will be logically aligned with every other sensor value of S2, because S2 has a shorter period. So this is all given by the semantics. And Lingua Franca is a language suitable for building real-time systems. So here I introduced two features for interacting with real-time. The first one is physical action. And a physical action is essentially a signal that comes asynchronously from the environment. For example, if we want to build a system with some button that the user can press, the pressing of a button can be modeled using a physical action. We don't know when the button press will come. We know that it potentially could come at any time. And whenever this button press happens, an event is created and injected into the runtime system to be handled. This is physical action. On the right-hand side, you see the deadline keyword. So deadline, I think many of you are familiar. Essentially, in this case, it's a feature to make sure that certain reactions do not start too late. If it starts later than this 50 millisecond threshold, we will invoke a deadline miss handler instead. So why is Lingua Franca potentially suitable for space applications? The key property here is determinism. So Lingua Franca has a deterministic semantics. A Lingua Franca reactor processes events strictly in timestamp order. Given a sequence of events as inputs, a reactor must deliver one correct sequence of reaction invocations. So to show you what I mean, here in our running example, we can give a timestamp, a logical timestamp T to the sensor calibration, our task A. And the ground, seeing that the satellite calibrates the sensor at time T, it can schedule an event slightly later at logical time T plus 10 seconds to change attitude. So in this case, task B at T plus 10 seconds. Then the Lingua Franca, the runtime guarantees that this timestamp order is delivered. Concretely, Lingua Franca ensures that the satellite first calibrates sensors, then changes attitude. By specifying two timestamps and by providing semantics that everything follows in timestamp order, we can make sure that we have the third behavior that we desire. So what's kind of important here is that Lingua Franca does the heavy lifting, not the user. So instead of letting the user augment the application logic to ensure reproducible behavior, the Lingua Franca runtime takes care of everything. In fact, the design principle for Lingua Franca is that the user need not worry about threads when programming Lingua Franca. So instead of writing a process function, as you see on the right, the user can write this program instead in Lingua Franca, and the semantics and the runtime should take care of everything. Also, Lingua Franca enables time-centric programming. So essentially, it enables the user to specify a desired timing behavior by designing an event sequence. In the system below, which has a similar layout than the previous example, we can see that every LiDAR frame is aligned with every other camera frame, because LiDAR has a period of 34 milliseconds, while the camera has a period of 17 milliseconds. So every LiDAR data point is aligned with every other camera data point, and this is all specified in the program. All right, so how do we implement Lingua Franca semantics? Currently, it has two types of schedulers. The first one is a dynamic scheduler. It's the default scheduler. It's available in all target languages, all 5 target languages, and it is a runtime scheduler. For more details, you can refer to these papers below. Another one is a fairly recent work. We recently introduced a quasi-static scheduler. It's experimental, only in the C target, and it's a compile time scheduler. So for the rest of the talk, the system is being built using this scheduler. And let me quickly expand on that. Since the timing and the dependency information is specified in Lingua Franca, this presents an opportunity for quasi-static scheduling. So what this means is that we can generate quasi-static schedules from Lingua Franca programs as bytecode. We can feed that bytecode into a virtual machine that we implemented called PretVM. And essentially, the bytecode contains information about the scheduling and the timing of our system. Then we can further compile the whole C project down, tailored for specific chipsets like STM32 and ESP32. There are currently 3 quasi-static schedulers supported. The first one is a load balance scheduler. As the name suggests, it breaks down the work evenly for the workers. The second one is an edge generation scheduler coming from this prior work. And this scheduler can guarantee that the end-to-end execution time within the hyper period falls below our high-level specification. And the last one is a Moccasim scheduler, which comes from this prior work, which is a design space exploration tool that can allow us to optimize for energy and execution time. So this is the instruction set for this virtual machine. As you can see, a few instructions are directly inspired by RISC-V, and there are some timing instructions such as delay until, DU. These timing instructions are borrowed from the Pret machine architecture, which is a previous project at Berkeley. So to compile Lingua Franca to bytecode, we start with a program, and we generate a set of state space diagrams from the program, which gets further compiled down to a set of unpartitioned DAGs, directly acyclic graphs. Then from these DAGs, we partition them using our static schedulers. In this case, we assume we have 2 cores or 2 workers, and we generate 2 partitions, one green and one blue. And for each partition, we generate a bytecode. And then we can deploy this onto a specific core. All right, lastly, I'm going to talk about this reaction wheel program as a case study. So on the left, you can see the setup in my office with 2 single board computers, and they form the satellite part. On the right-hand side, we also have a ground station running on the laptop. The satellite component has 2 single board computers. One is a Raspberry Pi 4B, which runs a reaction wheel controller. The other one is a Odroid XU4, which acts as a data processing unit. And this data processing unit can sporadically launch a file compression task, shown at the bottom. So the reaction wheel controller does 3 things. The first one is that it periodically pulls from an angular rate sensor and a gyroscope simulated by the Mujoko simulator. It also runs a PID controller to spin the reaction wheels in the simulation. And it also sends status to the data processing unit downstream. So at the bottom, you see the architecture diagram for this reaction wheel controller. And the data processing unit also does 3 things. It receives data from the reaction wheel controller. It communicates with the ground station. And upon request, it can launch sporadic compute-heavy tasks, such as compressing a set of data files. And here is a very quick demo showing that our reaction wheel in action. On the 2 terminals on the left-hand side, one runs on the Raspberry Pi, another runs on the Odroid. And as you can see, the ground station, which is on the right-hand side, is rendering a live view of the satellite, changing its orientation such that it's trying to approach a desired attitude. So in this case, X is trying to reach 1.0, Y is trying to reach 0.5, and Z is trying to reach 0.2. And as you can see, the system sort of stabilizes in the end. All right, yeah, it has pretty much stabilized now. Okay, so let me quickly talk about the file compression task. This task essentially represents a sporadic compute-heavy task performed on the satellite. Here we have 3 compressor reactors to perform compression in parallel on a set of 15 files, which amount to 330 megabytes in total. And because I mentioned that this program is statically scheduled, running on a virtual machine. We can use the Moccasin scheduler, this design space exploration tool, to optimize for the execution time and the energy consumption. So on the graph at the bottom left, Moccasin suggested 4 mapping strategies for this task. And we circle the optimal mapping strategy in the gold circle and in a suboptimal strategy using blue circle. And we can clearly see that the gold circle is performing the best, projected to perform the best, both in terms of execution time and dynamic energy. And what it does is that this mapping strategy maps the 3 compressor reactors, the 3 A15 cores on Odroid XU4, and the suboptimal mapping maps 2 compressor reactors to A15 and 1 to A7. And we compile the whole thing to C, and then we actually perform measurement on the execution time energy. We find that the optimal mapping does deliver the least execution time as well as the energy consumption. So to conclude, Lingua Franca is deterministic, making it a good fit for space applications where reproducibility and testability are key. Second, instead of letting the user manually augment the application logic, Lingua Franca does the heavy lifting. And lastly, Lingua Franca enables time-centric programming, enable a top-down design workflow that simplifies code validation and optimization. If you're interested in learning more, feel free to scan the QR code on the left, and we also have a website, lflang.org, which is on the right. Thank you very much.
Thank you. We have a few questions online. The first question, what's the source of time in Lingua Franca? Is there some sort of API for specifying the time source?
Yes. So Lingua Franca distinguishes logical time from physical time. So the source for physical time comes from the underlying hardware. So if you run on an operating system, the time source is the system clock. If you run on an embedded system, you can have specific peripherals to provide these very precise time values. Yes, it depends on the hardware.
Back on the original example of the 2 sensors that were combined into, basically combined, you had, if you could go back, actually.
Yes, I'm trying. Right here? Or even earlier?
Even further, yeah, sorry.
The code example. Yep.
Yes. Okay, so in the processing unit there, right, I understand the sensor, right, you have a reaction that's taking in a time that, you set from 0 to 100 milliseconds or 50 milliseconds, right? But in the processing, your reaction takes in, right, the 2 inputs.
Yes.
One's at 50 milliseconds, one's at 100. So does it only act on the 100, or does it act on the 50, and then, does it bring the previous 100 up to the 50, right? How does that interaction work?
Yeah, this is a great question. So the semantics of Lingua Franca is that, well, we call whatever that's wrapped in the parentheses triggers. So a reaction fires whenever any trigger is present. Okay. So in this case, when the 50 arrives, the reaction is triggered, and when the 100 arrives, it's triggered. And in the case where both arrives, the reaction essentially has access to both data values at the same time. So this essentially makes sensor fusion rather trivial because the semantics guarantees alignment.
Okay, thank you.
Thanks.
I'll take another online question here. One of the questions was, can any language be used, or is it designed to support only LLVM-related languages?
Yeah. So at this current stage, there are 5 languages supported as target languages: C, C++, Python, Rust, and TypeScript. Yeah.
There's a related question about whether it can be used with bare metal.
Yes, we have performed bare metal experiments on this embedded board called NRF52. Yes.
There's one more question. how does Lingua Franca manage resource sharing, message passing between reactors?
So message pass, so depends on the mode of execution. So Lingua Franca supports so we have a version of Lingua Franca which is called federated execution, which allows you to run Lingua Franca programs on multiple machines. You can also run them on a single local machine. So if everything's local, then we share messages through share memory. If it's federated, messages are being sent using sockets.
Thank you. Thank you very much.
All right. I'll also be answering questions on Slack.